4.3 Internet Protocol. Now you see here the section is a little bit long, so do we expect that we spend quite a bit of time here? Alright, so network layer is in the middle, okay, of the protocol stack. So what I'm showing here are again, the important functions to be implemented there. Forwarding, we've already talked about in 4.2. Routing being in the data plane, we'll only talk about it in chapter 5. Another thing we'll talk about in chapter 5 is this, ICMP. This is one of those management protocols. So just like routing, management is also one of the control plane functions. So we'll be talking about ICMP later in chapter 5. So what's left in chapter 4 is just this, IP protocol. In there, we're going to talk about this IP addresses. If you recall, in forwarding function, the traditional model actually checks what? The destination IP address. So that's definitely talk more about the address format. Okay? And in the modern forwarding, we do what? SDN. We could actually look at multiple fields in the packet header, okay, to decide where to go. So we do need to know a little bit better about the packet format. What are the header fields? So that's coming right now. Now the two most important fields, source IP address and the destination IP address, each 32 bits long. Second, the header checksum. Now the reason this is important is because we did have what, TCP or UDP checksum that would ensure the integrity of this part of the packet. What about this part of the packet, the header part of the packet? We needed a checksum here, okay, to ensure the header part is also, not having any bit errors. Now let's go over these individual fields one by one. So focus on the first row now. First field, there is called the version. So the packet we're actually showing here is defined in IP version 4. Okay, so the version number, therefore, will be 4 here, always. And then two other fields, header length and the length. So the header length here is to tell the size of the header. And the length here, telling the entire packet size. Last field in the first row, the TOS. Okay. It looks a bit familiar, isn't it? Because when we're talking about congestion control, there's this flavor called the network assisted approach. So we did introduce one mechanism that requires the use of the ECM bits. So these are 2 bits in the IP packet header, if you recall. This is explicit congestion notification. So those 2 bits are right here. Again, in the IP packet header. Now let's switch gear and take a look at the fields in the third row. Okay, first is here, time to live. So this field is very, very special. Okay, we've never seen it before, and it will probably make sense, only it's in the IP layer. Okay, so we would do this. We would decrement the value here, time to live, TTL, by 1, okay, after a packet passed through a router. Okay. When this value reaches 0, what we will do there, this router is going to discard the packet entirely. Okay. That is also saying a packet here, given n as the TTL, will only be able to hop n routers on the internet. Okay. And afterwards, it's going to be just dropped. So time to live here is kind of regulating, okay, how many hops the packet can travel on the internet. The reason we need this is because, on the internet, routing algorithms, okay, depending on how the messages are exchanged, depending on the computation process, we sometimes ended up having loops in the routes being computed. Now, in these cases, packets can actually travel the internet forever, like ghosts. Okay, so not good to have these ghosts. All right. So let's set a time to live so that they're more human-like. All right. So maximum number of hops the packet can travel. Second field in the third row, upper layer. Okay, so this is something that's slightly familiar because this is telling, okay, the network layer that after we extract the segment part, which place in the operating system we pass the segment forward. Okay, so the upper layer protocol, what is that function there? Okay, handling this incoming of a segment. Okay, so upper layer protocol to deliver the payload. It could be the UDP handler or the TCP socket handler. Now the second row. So these three fields in the second row are actually working together, okay, supporting each other. And it's for a very important functionality called the fragmentation and reassembly. The thing is that the IP datagram, when it enters the link layer, now the link layer actually defines a maximum packet size or maximum frame size. The packet in the link layer is called a frame. Okay? Now that size can very well be smaller than the IP packet size. So in that case, we need to cut a big datagram into smaller frames. Now these flags there, okay, are allowing us to reassemble the frames back so that we can recompose the original packet, original IP datagram. Last field, okay, here, the options. Now these are optional because it's usually for debugging purpose. For example, if we want to make sure that we track at which time point this packet traveled through a particular router, yeah, we could have the router adding a timestamp here. Okay. If we want to make sure that we know the exact path this packet is traveling through, now each router there in the middle can, sign here so that we know exactly which router, okay, this packet has visited already. Okay. Now, if you sum the header size together, okay, so each row is 32 bits, so it's 4 bytes each row, and we do have how many rows? 1, 2, 3, 4, 5 minimum, right? So that's at least 20 bytes. So the IP packet header itself, 20 bytes. Now we didn't count the TCP packet header explicitly, but it's also 20 bytes, right? So that's at least 40 bytes of header, okay, in a packet. Now if we are sending data that's very, very short, like 3 bytes, 4 bytes, the overhead, okay, of sending data with large header like this can be pretty high. Okay, so one of the problem in IPv4 is that the packet header there contains fields that might not be really necessary. So later you will see in IPv6, they will try to make it as concise as possible. So that is the IP packet format. There's one thing we're yet to talk about, the fragmentation and reassembly. Remember the second rows of the header fields. So those fields are related to this function, fragmentation and reassembly of the IP datagram. The reason we need this is this. Okay, packets, okay, as they travel the network, they might go over different network links. So for example, packet traveling the network like this. Now this could be an Ethernet link, this could be an optical link, and this could be yet another optical link, while this is another Ethernet link. So these packets might be going through different link layer technologies, running different link layer protocols. In those protocols, they might have different MTUs being defined. So this is the maximum transfer size, essentially the maximum packet size at the link layer. So different link types, different MTUs. Some of these MTUs can be smaller than the IP datagram size. In this case, we need to break the IP datagrams into smaller parts before passing out to the link layer. Now, some of you might be thinking, wait. Hey, didn't we do something like this in the transport layer, right? We take messages from the application layer, break the message into smaller parts, add the transport layer header, and that form a segment, and we pass it down to the network layer. At the network layer, what do? We break the segment into multiple parts, add the IP header, and then pass it down to the link. So why didn't we just do that, right? Because then at the link layer can just break the datagram, right, into parts and add the frame header. and such that it's smaller than MTU. Problem solved. You're right. It's just that the link layer protocols here. Okay. They are all quite primitive. And there's a good reason for that. That is because we do want packets to travel really, really fast on a link. Okay. So link layer protocol does not do the segmenting datagram implementation. So that's why the network layer there, okay, poor network layer. The network layer needs to break segments apart. For the transport layer, the network layer also needs to break the datagram apart for the link layer. Okay, so fragmentation reassembly is actually to do the link layer's job of breaking the datagram apart and reassembling them back. Now let's see how it works. A large IP datagram needs to be divided into multiple parts. Okay, when we run into a link that defines a smaller MTU. Okay, so one datagram will become several datagrams like this. Note that these smaller ones are not frames. These smaller ones are IP datagrams. All right. So we actually break them into multiple parts before passing it on this link here. Now these datagrams will remain the way they are through the network and comes into destination. The reassembly is only done here, only at the destination. Okay. So only the final destination is doing the reassembly. Okay. Now the breaking of the original datagram to multiple parts and the reassembly of the multiple parts back to the original datagram is relying on those three IP header fields. Let's go over an example to showcase the three header fields: ID, fragmentation flag, and offset. The example says we do have a large datagram for 1,000 bytes, and we're running into a link with MTU being 1,500 bytes. So let me show you the result, okay, straight. So this large datagram is now fragmented into three smaller datagrams here. Okay. And so 1,500 is the maximum transfer unit size. So each, less than 1,500. You see there, the three smaller packets will all be carrying the same X. Yes, you're correct. So X is there. So the ID field there is used to identify which of these packets belong to the bigger, okay, datagram originally. Second field, you see the three are in sequence. First, second carries the flag 1. Only the last one carries the flag 0. So the one carrying the flag 0 is the ending packet, ending datagram. Now, these two would both be carrying 1, saying that they are actually earlier datagrams. But which one goes first and which one goes second? You can actually look at the offset. Okay, those carrying smaller offsets are earlier. In fact, what the offset is saying is the position of the first byte here in the original data packet. Okay, so first byte here is the original byte 0. First byte here is the original, byte something. Okay, it's not exactly 185. It's actually 185 multiplying 8. Okay, so the offset is actually counting 8 bytes at a time. Okay, so that is a way to try to make sure the offset field is a little bit narrower. Because then, 1 byte packet, that is just not making sense. So there, you get it. This is IP fragmentation and reassembly. Okay. Oh, and by the way, okay, if you multiply 185 to 8, you get 1480. And that is because of this. Okay. There's only 1480 data bytes in the first packet. Because, hey, IP packet header is 20 bytes. So total length being 1500, data can only be 1480, right? So as I mentioned, 185 is indicating the position of the first byte in the packet. But the position should be divided by the A. Okay, the original position divided by A will be the offset value. Therefore, offset multiplying by A, the original position.